little bit more about floating point stuff. So, of course, last time we talked about the Ieee encoding, right? So how we actually store this data. And let's just remind ourselves the encoding for 32 bits was a sign bit, 8 bits for the exponent, biased by 127, so they look larger than they actually are. And the hardware reason for that is it makes it easier to compare the sizes of two exponents without having to do as much arithmetic. And then 23 mantissa bits, so that's the stuff that goes after the radix. And of course, the convention is that in scientific notation, right, you don't have to write the 1 that's in front of the radix because, well, what else is it? It can't be a 0. There's only one other bit left, so it's got to be a 1. So even though there's 23 mantissa bits that you encode, there's really 24, right? The 1 point, you get the 1 point for free. Okay, great. And then everything works the same for 64 bits, except there's 11 exponent bits, however many of the, whatever's left is the mantissa bits, and then the bias is 1023, okay? But same system, just with more bits. Okay, great. And, okay, so for example, let's see, 2.5 would get encoded like this, right? Sign, exponent, mantissa, and they always go in that order. Okay, and then that float toy thing that I showed you guys that's on GitHub is pretty handy for demoing it. So, okay, so like I said, same thing for 64-bit, except just more bits. 11 exponent bits, biased by 1023, and then the remaining 52, I guess it is, mantissa bits. Yeah, so the encodings end up working. So this is actually kind of one of the nice parts about the bias being different for each number. Notice what the, oh, I'm sorry. Notice what the pattern is here for 2.5 in 32-bit encoding, right? 0, 1 followed by a bunch of zeros, and then the mantissa 0, 1 followed by a bunch of zeros. That's actually the same in 64 bits, it's just it takes more bits to do it, okay? So the what this means is it's not actually hard to convert a floating point number from 32 to 64 bits. Essentially, all you have to do is just slot in extra bits in the appropriate position. So the conversion is actually, if you've got a 32-bit and you want to convert it to a 64-bit, you just got to put, you know, the zeros in the appropriate places to pad it out to take all 64 bits. So that's kind of handy. Okay, but what I wanted to do then is talk about the, let's see, where is it? Talk about arithmetic later. Okay, so how do we actually do all this stuff inside, like actually use the computer to compute all this stuff? So I kind of lied to you guys last time. So we've got 32 of the either X or W registers, right, depending on which size you're talking about. On the floating point side, there's actually 32 registers that are called V for vector, and they're 128 bits wide. Now, you can subdivide these things into a bunch of different little chunks, and we'll talk about one other subdivision method later. But the first way is if you just care about doing regular floating point arithmetic, then like the difference between W and X, right? W is 32-bit, X is 64-bit. We've got sort of the same thing on the floating point side. You've got 32 S registers, which are 32 bits for single precision 32-bit floats, and 32 D registers, which are the same thing, 64 bits wide for 64-bit double precision, so hence the S and the D. There. Where's Drake? Oh, I don't know. I guess somebody's getting fined a gentleman coin. Yeah. Anyway. So, and the relationship that they have is exactly like the W and the X's, right? The W and the X, like W0 and X0 are not completely separate objects. W0 is sort of the lower half of X0, right? Same thing with the single and the S and the D. So S is the lower half and D is the 64-bit half or chunk. Okay. And then they all sit inside the V. So the ordering of this is you've got the V registers, which are 128-bit wide. Those are the big chunk. Within that, you can do the lower 64-bit as a double, the lower 32-bit as a single, the lower 16-bit as a half, and the lower 8-bit as a byte, right? So you can subdivide these things actually in a lot more ways than before. So for right now, we'll concentrate on either the S or the D version, and then later on, we'll look at sort of how you can pack these things in and do a lot of arithmetic a lot faster than you would think that you could. So anyway, so let's see. Okay, so we've got the operations that we would need. Well, okay, a lot of them are going to load. This should be D0 here. Are going to look the same as the floating. I mean the integer variants, but there's a couple of differences. Okay, and this is actually where we'll have to be a little bit careful because some things work exactly like an integer side and some things don't. Okay, in particular, if I want to load D0 with data that's at some address, well, I do it just like before, LDR. Okay, no big deal. The immediates part, though, is a little bit more of a problem, okay? And let's think about why these two instructions may not work the way we think that they do. Okay, what does it take to encode 2.5 as a 32-bit or 64-bit number? As a float, right? Well, either 32 or 64 bits, right? All right, so let's say we take the 32-bit version. How wide is every instruction in this architecture? All right, so 32 bits, but if I need a 32-bit immediate, what's going to be the problem? I don't have room for it, okay? So I can't just, oh, better late than never, Drake. We were getting ready to fine you a gentleman coin. Huh? Yeah, okay. So you can't just F move everything the way that you would expect, okay? And so what you have to do is something a little bit different, okay? So let's say, for example, that I want to, and just because I'm lazy, let's see, this is our 32-bit float. Okay, so that's 2.5. So I'm going to be lazy and I'm going to copy it here. Let's see. Let's see, I don't want Word. It's, oh yeah, that is Word. Okay. So I can actually save numbers up here also in the data section the same way that I would strings. Okay. And in this case, the instead of ASCII for an ASCII encoded string, I'm storing a word, which is a 32-bit object, and there it is, right? Okay, so that guy. So what I would have to do, so if I tried to do something like, well, first off, let's get the usual. Okay, so let's get the usual stuff in there, right? So let's say that I wanted to do the following. Okay, so let's see. Let's say I have a string. Okay, and I'm going to print this number. Okay, so let's say that all I want to do is print 2.5. Okay, let's say that we tried to do this with fmove instead of what I'm going to show you in a second. Okay, so if I wanted to say something like this, right? Then to print it, what I need to do is this, right? So I need to load S0 with my number, load the address of the format string here, and branch to printf. Now we're going to see that this actually has a couple of issues, but we'll talk about those in just a second, okay? So let me save that, and let's compile it real quick. And let me scooch this a little so you guys can see both pieces at the same time. One of these days I'm going to get even fancier and have it so that like my stream can switch between multiple screens, and I'll have like a really awesome background and the thing where you can like donate gentleman coin and yeah. But you know, like the big streamers that have all the like stuff and okay, so let's see, where were we? Yeah, they have all the stuff. Okay, so, and I'll go ahead and do it with debugging just so that we've got that. Okay, so what happened? Yeah, our number is most certainly not 0, right? But it printed 0. Okay, why? So now this is one thing that I'm not really sure why this is the case, but it is. When we printed integers, what did we have to use for our in our format string? %i or %li, and what was the difference? Yeah, %i was for a 32-bit integer, and %li was for a 64-bit integer. And we had a different format string, you know, thing, %i or %li, depending on which one we want, okay? So I put %f here, and you guys probably were like, oh, yeah, that makes sense, right? It's a float, right? So I'm printing a float, no big deal. So it should be %f. Okay, there is no distinction between printing a 32-bit or a 64-bit float. Maybe better put, you always print a 64-bit float. What's the problem? Ours is 32-bit, okay? And so if we think about how it's encoded, right, if we have, say, our D0 and our S0 that sits inside of it, so D0 is the whole thing, and then of course this chunk is S0, what was our encoding for the number? It was 0x402 blah, 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 right? And the encoding, if I take the entire D0 chunk, it's got 32 bits worth of zeros in front of it. Okay, so is the number that's in D0 actually 0? No. But what do you think is going to be the case if you've got a crap ton of zeros in front of some stuff in your mantissa? This is actually something times 10 to the minus 1023. Okay, which is such an exceedingly small number that if we print it, and we only have six digits after the decimal point, it looks like 0, okay, because it's so ridiculously tiny, but it's not actually 0, okay? So Gucci there. All right, so if I want to print this thing correctly, what I have to do is I have to convert 2.5 from a single to a double and then print it, okay? So does it make sense what the issue is? What do you mean LF? Oh, like long float? Oh, well, let's find out. Nope, you can't. Okay, LF actually isn't a valid thing. Okay, that would be nice, right? Is that if we had, you know, float and double in the same way that we had 32-bit and 64-bit integer, but we don't. Yeah. Um, sort of, except the encoding. Well, here, let me actually just do it this way. You can't just shift like that with floats. With integers, yeah, we totally could. But okay, so here's the issue. Oops. Right. We could shift the bits, okay, but the problem is we can't just shift the bits because the exponent field in 64 bits is 11 bits, but it's only 8 bits on the float. So if we just shoved all the bits over by 32, you know, shoved them 32 bits to the left, we would have, if we put 4020 here, right, to match, then we would actually be encoding 8, not 2.5. Okay, so unfortunately, it's not that easy. That'd be nice, but c'est la vie. Okay, so what we have to do instead is just convert, and the way that we do that is with fconvert. So what that will do is take either a 32-bit thing and 64-bitify it, or vice versa, at the risk of course, of truncation, right? So if you convert a 64-bit float to a 32-bit float, what could happen? Yeah, you might lose some precision. Now, with a simple number like 2.5, we wouldn't. But if we were trying to be really, really precise with something, then that could be a problem. Okay, yeah, pardon. Which would be smarter in this case, right? Is to just, but see, then I would have to, up there at the top in the data section, I'd have to change that and give it not a word, but a D word, and give it the 64-bit encoding. Right? So for the sake of this example, yes, this is silly to do it this way. Okay, but if I'm doing 32-bit arithmetic, then I've got to have a way to convert it. Yeah. So that'll just take a 32-bit float and expand it to a 64-bit float, or vice versa, right? At the risk of loss of precision. Okay. Now, we wouldn't lose any precision, but you lose no precision going from 32 to 64. That makes sense. You've got more bits now. And also for a number that's simple, like 2.5, there's going to be no issues. If you had something like pi to a whole bunch of decimal points, then that would be an issue in terms of precision loss. Yeah. 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 F move is going to use the floating point registers instead of the regular ones. Yeah. Hmm? Yes, from F0 to D0, because remember the destination gets listed first. Okay, so this is going to convert it to a 64-bit. and then, and of course now it works fine, okay? All right, so in this case, we were able to use fmove, okay? But let's say that I change this to something like that, okay? Huh? Well, okay, that's the printing of it, right? I can change that by, right? So printf by default with a float will print 6 digits after the decimal point. Oops. Okay, so now if I try to assemble it, what happens? Yeah, it says invalid floating point constant, 2.51, blah, blah, blah. And essentially the issue is what we just said, right? That if my fmove instruction has to be 32 bits wide, and of course I need to spend some of those bits on the opcode that says it's fmove and so on, there's not 32 bits worth of space to pack in the immediate. And if I want to encode something precise like 2.54, blah, 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 there's not room for all of those bits, okay? And so, maybe I could back it off a little bit and try something like this, okay? But it's still not going to work, right? And so you can't do everything with fmove. You can only do like really, really small is not the right word for it, but only 1 or maybe 2 decimal points, right? See, I won't even do that. So it'll take 2.5, but not 2.51, okay? Now, that doesn't mean, of course, that you can't use the number 2.51. It just means you can't load it with fmove in an immediate. You have to do something else. Okay, so is that all right? Yeah? I mean, it's annoying, but, that's just the way it's going to be, right? Sorry. Yeah, Drake. Mm-hmm. That's what we'll have to do is actually a pair of LDRs, okay? So first off, let me go back over here to float toy and let's get 2.51 as an encoding, okay? Which happens to be this, okay? And now you see why we have an issue, right? Because can I truncate any of this? No, right? I need all 32 bits worth of stuff to properly encode this number. And now, actually, are you guys surprised that this has that much junk at the back for 2.51 versus 2.5? Why isn't it surprising, Owen? Right. So the 0.01 part, 1/100th, is easy to express it as a base 10 fraction, 1 over 100, but you have to express everything here as a sum of base 2 fractions, right? And so, yeah, you got to go out a long way. All right. So what we have to do instead, so what was the number? That, right? Okay, so I can't do this anymore. I'll still have to do the fconvert. And so what I'll have to do is I'll have to load x0 with the address of my number, just like we did with strings, right? What's the address of that thing? And then we'll load S0 with the contents of memory pointed to by x0, right? So I've got the indirection with the brackets. Okay, so does that make sense? Yeah. All right, and so then no problems with assembling, running, and I get, 2.51. Okay. Now in this case, I told it to do 10 decimal places. I didn't need all 10 here. So you see how there's space there? That's where the rest of the 10 are. Okay, So the 10 means 10 digits, regardless of where the decimal point is. And so that's why there's that little space there as opposed to here where there was only one space, okay? All right, so you can't just F-move anything you want. Some stuff you can, but most, useful numbers you cannot. And so you have to do, kind of like we did with strings, do a pair of LDRs, one to get the address and the other to actually load it from memory. Okay, good? Oui ou non? Okay, great. All right, now, one other thing, is anybody bothered by the fact that I've got the the number in D0 or S0 and I'm printing? Would you expect it to be in D1 or S1? Okay, if this were following the integer pattern, it would be, okay? But why is it that we can put it in D0 or S0 instead of having to put it in D1 or S1? Well, it's because the S and D registers are completely separate from the integer registers, right? So what has to go in X0 anytime you want to print anything? Address the format string, right? That doesn't go in D0. Why would you put an address in a floating point unit? Well, you could, but right, but that doesn't make sense, right? So, so in this case, right, you start at the lowest available register for printing, right? And because D0 doesn't have to get used to store an address, you can just put your number there, no problem. Okay, good? Oui or no? All right, excellent. So let me pop in a GDB with this thing real quick. Because I wanted to point out how we can do the debugging. I can look at F0 or D0 or sorry, not F0. I can look at the contents of any of the registers the same way that I would with the integer ones. So if I say info R S0, then what's loaded into that? Yeah, the number, right? And it will decode it for me. And I can see that, okay, as a float, what is my number? 2.50999999 repeating. Okay, and basically what we're dealing with there is the lack of precision or the limitations of 32-bit precision. You can't get 2.51. The closest you can get is basically the 0.9 repeating. Oh well, c'est la vie. And then it happily is nice and is decoding it also as integers. So the U and the S are for unsigned and signed. There, in case you wanted to know what it was as an integer. Which why you would want to do that, actually in a moment will be sometimes useful, okay? But anyway, you can inspect the S and the D registers just the exact same way that you would any of the integer ones. You just say info R and then whichever register you want, right? Okay, so there's that. And then actually we're about to execute the fconvert function. So right now, what does D0 have in it as a floating point number? It has this, right? Blah, blah, blah times 10 to the minus 315, right? Which is why when we printed it earlier, it appeared to be 0, because something times 10 to the minus 315 might as well be 0 as far as we're concerned, right? Okay, so if we step one more time and then look at it, now look what we've got. Yeah, it's up-converted it to a 64-bit number, but we have not gained any extra precision by doing the conversion. We'd have to go back and like re-encode 2.5 as a 64-bit to get that extra precision, and it turns out to be, you know, blah, 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 right? 2.5099, blah, 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 blah. Okay. All right, so does that kind of make sense? All right, so the TLDRs, right, is you can't F move everything, and anytime you want to print, you can only print a 64-bit float. So if you're working with 32-bit floats, fine. When you want to print them, you have to convert them to 64 bits just for the sake of printing. Okay. Now, if you're working in 64-bit arithmetic from the get-go, you don't have to worry about this because, well, it's already 64-bit. Okay, but if it's 32-bit that you're working with, then you have to do that. Okay. All right. Gucci. And if you want to do a 64-bit thing up here in the data section, you just put D word for double word. Okay, so that's a 64-bit thing. And then whatever encoding you know of your number that you want. So this float toy thing, of course, is going to be a godsend, right? If you needed to encode pi, for example, right, and you're like, well, right, what is pi? Well, then it's going to give it to you, right? And you don't have to sit down and actually convert it by hand. However, should you guys be able to sit down and convert these things by hand? Yes, for simple numbers. I'd give you something like 2.5. I'm not going to give you something like 2.51 because I'm not a jerk. Okay. Yeah. So, so you guys should be able to encode and decode simple 32-bit numbers. I won't make you do 64-bit simply because it's the same thing, but there's just shit tons more. Well, 32 more digits. And what if you can do it in 32 bits? Can you probably handle it in 64 bits with more paper? Yeah. All right. So back to yeah. Let's go back and start looking at. Okay, so the operations that we have, we just talked about this, right? Um, pretty much any of the operations that you had in integer land, you also have in floating point land, just throw an F at the front of them, okay? So in particular, right, you can do addition, you can do fused multiply and add, um, and these can either be with D or S registers. Um, it all works pretty much identically to the integer side, except it's using the floating point versions instead, right? So nothing particularly special there, but what you do get are some instructions that obviously don't make sense in the integer department. For example, square roots, right? Doesn't make sense to do integer square roots because, well, most of the time you're going to get something that's a number that's irrational, and you can't do that as an integer. But you do have things like f square root, okay? Um, and obviously that's, you know, handy. There's division, right? Multiplication, square roots. There are actually hardware instructions on this architecture for exponents and logarithms, which is kind of handy. Okay. Back in the day, of course, there weren't such things, and so this is why, um, you know, like in when you guys are doing stuff in Python, does anybody had to, you know, load in what was it, SciPy or what's the math library? Yeah, right, or NumPy or whatever, right? You have to load in those libraries that have software routines to do sort of some more advanced mathematical kinds of stuff, uh, uh, because there may or may not be hardware instructions for those things. There are actually for some stuff like square roots or um, exponentials, logarithms, but there's not stuff for, like, for example, trig functions, right? So there is no hardware trig function. Um, you have to do something different for that, which is kind of complicated, but you have to handle it in software is basically the point. So of course, back in the day, right, like in the 80s, you had no floating point anything, and you had to do all of it in software. And as you could imagine, doing it in software involves a lot of bit banging, meaning, plucking out bits and doing stuff and, manipulating things as integers and then putting it back into some sort of floating point thing. And as you could imagine, this would be slow compared to if you had dedicated hardware for this thing, okay? Yeah, you can also do floating point comparisons, right? So, in the same way that we could say, all right, if the number is bigger than 5, do one thing, otherwise do something else. How did we do that? We compared one register to another or one register to an immediate. You can do that with float, although you just throw the F in front for floating point comparison. Okay, and that thing is going to set the condition flags kind of like compare does. And so you can do branch instructions based on floating point values if you needed to. So for example, let's say that you were writing something that was going to do like a square root, right? What might you use the comparison if you were writing a thing that does square roots? Yeah, make sure the input's not negative, okay? Or, if you had some other mathematical function, to make sure that you had a valid input that wasn't going to cause, wasn't going to give you an undefined problem, like with a logarithm or something. Yeah, so that's why you would use it. Okay, let's see what else I wanted to say. Okay, I'll talk about this later. I want to talk about a little bit of floating point voodoo. Okay, so let's take, just for sake of example, let's take the square root of 2. All right, what is that as a decimal approximation? 1.414 blah, 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 right? Okay, but 1.4 is maybe a good first approximation, right? All right, so let me take the number. So I know that this is 1.4 blah, 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 okay? So let's just say that we guessed 1.4. Now that's not a very good number, and actually, just for sake of demonstration, let me guess 1.5. Okay, now I know that's not as good of a guess as 1.4, but for demonstration, this will be fine. All right, so take 1.5. Okay, so that's my first guess. All right, then I'm going to compute the following. I'm going to take 1.5 and 2 divided by 1.5 and average those two numbers. Okay? All right, so in this case, the arithmetic would be easier to think of in fractions, right? Because this is 3 halves plus 2 divided by 3 halves all over 2. So what's 2 divided by 3 halves? 4 thirds, okay? So I've got 3 halves plus 4 thirds all over 2. I'm going to have to do some common denominator business, right? So this would be what, 9/6 plus 8/6 is 17/6 over 2 would be 17/12. Okay? Now, what is 17/12 as a decimal? Somebody pop open a... Right? So 1.416 repeating, which I think you guys would agree is more accurate than what we started with. Yeah? Okay. Now, how could I make this answer more precise? Could I do this exact process again? Yeah, but I would use the 1.416 number this time. Now, the arithmetic obviously would be a bit more of a pain in the ass to do 1 over, or 2 divided by 1.416 blah, 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 blah. Okay, but could we do that? Okay, so this iterative method, right, will improve the estimate once you make an initial guess. Now, the floating point square root function that the processor has actually is pretty dang good at giving you a good initial estimate, like a really good initial estimate. But if you really wanted to improve it a little bit, you could always do this. Does anybody know what this method is, by the way? So, and the 2, by the way, matches, so this 2 matches the thing that you're taking the square root of. So if I was doing the square root of 3, I'd have 3 divided by whatever. Does anybody know what this method is? Yeah, it's an instance of Newton's method, but it's even cooler than that. How long has this algorithm been in existence or known to humanity? Not quite 20,000 years, but 4 or 5,000 is probably a pretty reasonable estimate. This algorithm was known to the ancient Mesopotamians, right? So in Babylon and whatnot, right? So think Epic of Gilgamesh kind of time period, right? They knew this. It's kind of crazy, right? Yeah, and in fact, there's tablet evidence for this sort of thing. So we know that they knew how to do this, but it is just a particular instance of Newton's method from calculus. So anyway, yeah, so you can do that to yeah, you can do that to improve estimates, right? All right, now let me show you this. I love demoing because this is just mind-blowing, right? Now, early on in the semester, I did a colloquium talk about this algorithm, right? And I talked about like the math as to why it actually works, but let's look at it from a programming standpoint. All right, so what about if you wanted to do 1 over the square root of a number? Well, what would be one solution? Just compute the square root and then do 1 divided by that, right? That certainly work. If you've got a square root hardware and you've got a floating point unit, then go for it, right? Okay, what about, why would you maybe not want to do it that way? Okay, so what's the issue of doing the square root and then doing 1 divided by it? Possibly. Well, yeah, you're going to lose accuracy no matter what, but yeah, but you could of course always check in advance for that, right? Because if the square root is 0, that meant that the number you started with is 0. So I guess let me rephrase. From a speed perspective, why might doing the square root and then 1 divided by it not be a good move? Yeah, and in particular, what happens if you don't have a hardware square root or a hardware division capability, right? You have to do this in software. It's going to be slow. All right, so let's flash back to the 90s, where we did have hardware floating point units, but not hardware square roots, at least not in most processors that were available in the mid to late 90s, okay? And the division operations, right, the floating point units were slower than their integer counterparts. Makes sense. So you do a trick. All right, so let's take a look at this piece of source code, okay? So this is from Quake 3 source code, 1999. So the code itself was probably written in 98 or 97. Well, that's obvious, right? Doesn't that make sense? Yeah, the comments make sense. Okay, so yeah. So what I want to do is kind of talk about how would we implement this in assembly, right? I mean, we've got the C code, right? We could always program that. Um, there's one other thing maybe to mention here is when in C, when you say float, what does that mean? 32-bit, not 64-bit. If you wanted 64-bit in C, what would you type? Double, okay? But this is one of the things you have to be a little careful about when you're reading old code, right? So this code is what? 23 years old, almost 24, right? What is a long?
At the time, it's probably just an int.
It was a 32-bit, yeah, integer. Okay, so at the time, long meant a 32-bit integer. And a regular 32-bit int would have been 16 bits at the time. And that's just, why is this the case? Well, I mean, for example, an int, when you were in the early 80s, everything was 8-bit on most machines. Okay, and then processors became 16-bit pretty quickly and 32-bit pretty quickly after that. And so, some of the units had to get redefined. And yeah, so a long to us would be a 64-bit thing, right? Which is why, I don't know, maybe you guys have seen me in a few occasions do long, right, for a 64-bit thing, and that's just because it's out of habit, right? When you learn to program, back in my day, a long was 32 bits, right? Not 64 bits. Get off my lawn, okay? All right, so what's happening here, right? We're going to talk about how each of these instructions will kind of carry over into assembly, okay? And if we sort of parse all the different parts of it, well, the top 5 lines are really nothing special, right? We're defining a constant of 1.5. We're taking a number and multiplying it by half. We've got the number. Okay, so all of this, these top 5 lines are nothing exciting, right? They're just defining numbers. The stuff that's underneath of it is the magic, okay? And in particular, these 3 lines here that start with evil floating point bit level hacking and WTF, okay? What's happening here is, well, let's think about what the pointers and stuff mean. Okay, why is the value that came in the number? Okay, it's a float, right? So what is ampersand y in C? Yeah, it's the pointer. It's the address of wherever that floating point number is currently stored in memory. Okay, whatever it is. Okay, now, if I take the contents of that address, I just have a bit pattern, right? And if I interpret that as a floating point bit pattern, then it's a floating point number. But could I just temporarily pretend that that number is actually an integer? Like just take that bit pattern and say, okay, if this were an integer, what would its value be? Sure, okay? And that's what that line is doing. It's just basically saying, okay, take the floating point bit pattern that's stored out in memory over wherever, and just load it in and assign it to the value I, and pretend that that's an integer. Okay, now, why would you do this? Is a completely separate question. But if you wanted to do it, you could, right? In the same way that I could like take this 4020 blah, blah, blah that encoded the number 2.5, and I could say, okay, as an integer, what is this? Now, it's obviously not going to be 2.5. It'll be some really big number, but I could do that. Right? Okay, and then the WTF line is the fun one, right? All right, I double arrow 1, what's that going to do? Yeah, it's going to do a logical or arithmetic shift right by 1 position, right? So it's going to take the bit pattern and just shift everybody, okay? No big deal. And in integer land, what is that equivalent to doing? Okay, so if you take in integers and you shift all the bits right by 1 position, what's that the same as doing? Dividing by 2, right? In human arithmetic, shifting all the digits would divide by 10, right? In binary, if you shift all the bits by 1 position, it's tantamount to dividing by 2, or multiplying if you go the other direction. right? So in a demonstration, of course, of excellent comedy routine skills, right? You know, so what's the secret of good comedy routines? When you go back and you reference something from earlier in your comedy routine, okay, so in this case, what's the earlier thing in my comedy routine that has to do with the shifting? You guys remember my stories of when I used to work at Kohl's? Yeah. Did I not tell you guys this? The 10% thing? Yeah. Super genius because I could move a decimal point and tell her what 90% off of various items were, right? Okay, so anyway, right, so all that's doing is basically a division by 2. And of course, discarding any remainder. Now, the minus sign, okay, we're going to subtract this thing as an integer from something, okay, whatever. 5F3759DF, that's the WTF part of this. Okay, where the hell did that number come from? Okay, for that, you can go watch my math colloquium, or CS colloquium, I guess, okay? But what we're gonna do, right, is shift by 1 and subtract it from this very cleverly selected constant, okay, that looks like it's coming out of thin air, and at least as far as this source code is going, but isn't really coming out of thin air, right? It's coming out of very thick, dank air where you have to kind of float in the cloud for a little while before you figure out why that's the right constant. Okay, and then the line after that, well, if I can take a bit pattern and pretend it's an integer, could I take a bit pattern and pretend it's a float? Yeah, it's kind of the same thing, right? Ampersand I does what? Says, okay, this number I is out in memory somewhere. Take what's at that memory address and pretend it's a float. Okay, and there we go. All right, so what I want to do just to demonstrate this algorithm is let's start with what's 2 as a floating point number. All right, so if I just want the number 2, right, 4 followed by a bunch of zeros. Oops, I want you. Okay. So let's do this on the board. All right, so if I take, so my number, so 2 is, what is it, 0x4000, right? Pretty easy, okay? And what I'm trying to do with this algorithm is to compute 1 divided by the square root of 2. Okay, now, what is 1 divided by the square root of 2 as a decimal? I happen to know this number really quickly because 1 over root 2 is the same as root 2 divided by 2, so it's half of the number that we had over there, right? So if root 2 is 1.414 blah, 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 then 1 over that should be 0.707 blah, 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 okay? Happens also to be the sine of 45 degrees, which is why that number is something that's burned into my brain. Yeah? Guys like trig? Yeah? Okay. So, if I shift this to the right by 1 position, what do I get? And now remember, this is in hex, but I'm doing the shifting as binary, right? So, well, what do you think? How about this? Yeah, does that make sense? Why it would be that? Well, okay, because what is 4 as a hex thing? 4 is really, right, that. And I shift every bit 1 position to the right, so now where's the 1? In the 2's place. And so I get that. Yeah? Okay, so then let me write that number again here for convenience. And what was my magic constant? 3, can you read it off, Caleb? 3 F the magic, this number. Oh, sorry, 5F. 5F 37 sorry, 759DF. Okay. All right, so whatever that number is. All right, now subtract these things as integers. All right, this is the other reason that I picked 2 as my starting number, because the result of this subtraction is really easy, right? What is it? It's just going to be 3F3759DF. Yeah? Okay, now pretend that that number's a float. Let's decode it. Well, I don't know what the hell it is. If only there were a little website that a guy named Evan had programmed, and that we could like type in things and it would tell us what it decodes to. So 3F3759DF. Damn. That's pretty good. Okay, and I promise I didn't cherry pick this number, right, so that it would work. Okay, you could pick another number and do this, and it'll work. Okay, all right. Now, what were we expecting to get? Like the exact answer, if you will. 0.707 blah 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 is what we were kind of hoping to get. Obviously, we've kind of overshot it by a little bit here, but all this trick did was give me an initial guess. Could I improve that guess by maybe doing some Newton's method? Yeah, okay. And what it turns out in this case is that the Newton's method is that line there. Okay, so Newton's method is a general technique, and if you apply it to a specific problem, you get different versions, right? So Newton's method applied to this problem looks like that, whereas Newton's method applied to the regular square root problem was this Babylonian trick. Okay, so is that cool? All right, so you run through an iteration of it, and it will improve your estimate, right? Now, it's still only an estimate, but if it's really, really, really close, then you call that a win. And what about if you want to make it even more accurate? You do it again. Okay, what did Carmack do here? Did he do it again? No. In fact, the code's still there. He just commented it out. Okay. And so, you know, maybe do this tonight just to kind of see how it works. If we were to do this one more time with the estimate that we just got, okay, how much better would the estimate be? A few more decimal places, probably. Okay, but good enough. Okay, and that's where we have to kind of talk about with numerical methods of any sort, and this is certainly one of them. There's a trade-off. Okay, you have basically a continuum. You want an answer really quickly, or you want a really, really accurate approximation. Okay, and so what you have to decide is where on the continuum you are between how much work you want to do and how accurate do you want to be. If you're not willing to do a whole lot of work, you're not going to get a very accurate number. If you want a really accurate number, you have to do a whole bunch of work, right? So where are you on that continuum? Well, that might depend as to what the hell you're trying to do with your code in the first place, right? So what is this piece of code actually doing for Carmack, right? Well, it was from Quake 3, which is a video game, right? And video games need to run fast. Yeah? If you ain't getting 60 frames a second, it's trash. Right? Okay, and so that's essentially why he was able to remove this last line, is because, well, for the purposes of the video game, it was fine. okay? And now this actually is a research question I have. So I managed to get a hold of an old Pentium 2 system. So that would have been, um, you know, late 90s in terms of hardware. So I think I built a Pentium 2 computer for myself. Oh goodness, was it 98, 99? Yeah, I think like spring of 99, like January or something. I had a Pentium 2 350 megahertz. Oh boy. Or maybe it was the year before. I don't remember. It's a long time ago. Um, and so one of my research questions, I guess, is just like if, so the source code for Quake 3 is freely available, right? They open source this stuff after the game and the engine have made their sort of commercial, they've made all the money they're going to make, and the industry has moved on to better stuff. So Carmack open sources all of its old engines. So you can get the entire source code for the game engine. So what I'd like to do at some point is go through, take the code and uncomment that out. That's the only change. And then run the game and see if there's any noticeable performance drop or noticeable graphical quality increase. Like, could you even tell if that was changed? My guess is that on period hardware, yes, you would be able to, because he commented it out in the first place, right? But I don't know, right? Fortunately, I've got a Pentium 2 laying around in the lab up in Goodrich, so I'll have to fire it up. Now, on modern hardware, no, you'd probably never notice because they're so damn fast nowadays. But on period hardware, no idea. Okay. Okay. Good. Yeah. All right. So let's talk about how we actually do most of these instructions. Okay. Um, Now the first 5 are pretty easy, right? You're just loading in a specific number or multiplying something by half. Yeah. The F just means 1.5 is a float. Yeah. So I don't think you actually have to put 1.5 F. I think you could just type 1.5. But the advantage, so what actually happens here with the compiler is the compiler is going to figure out, okay, you want the number 1.5. What is that actually encoded as a 32-bit float? Like, what's its bit pattern? And that's what's actually going to get stored. So that value gets pre-computed at compile time, and that way you don't have to do it at runtime. Because if it's a constant, right, it doesn't need to be different. Okay, so good. So let's talk about how we're going to encode this stuff. All right, so that means we get to come over here. Okay, so that's our source code, right? And the hard part is the typecasting, okay? So this is taking a bit pattern that you think is a floating point number and treating it as if it's an integer. Well, the fmove instruction does that because fmove takes a bit pattern from one register to another, but it's not caring as to what type of data it is. It's just moving it from one place to another. Okay, so if I do fmove and take S0, which is a 32-bit float, and I put it in W0, all it does is copy the bit pattern into W0, the integer. That's it. Doesn't convert it, doesn't do anything. It just literally moves the bit pattern from one place to another. Okay, so that single instruction in C is sort of equivalent to doing the fmove instruction here. Okay, good. Um, then we need to do that. Okay, so how am I going to do that subtraction? Well, I need to separate this out into 3, kind of 3 or 4 pieces. Okay, The first thing I need to do is I need to take that thing and shift it right by one position, right? Okay, and so what instruction is that? Well, that's the division by 2, but I'm doing this in integer land, so I don't want to use the division operator. I want to use a logical shift. Okay, so LSR by one position, right, just shifts everybody one position to the right of my original number. Okay, now I also have the two instructions at the top, the move x1 equals magic 32. Well, what would I need to have up in my data section for this to make sense? Magic 32 is a word that has the value 5F3759DF. Okay, and so that first move instruction is just going to load the address of that into x1. Okay, and then what does the LDR do in the next step? Yeah, loads whatever x1 is pointing to, namely my magic number, into W2. And then on the last instruction, I can do the subtraction. Okay, so that single line of C becomes basically these 4 lines of assembly. Okay, basically load in the magic constant, shift the magic integer or the weird integer to the right by 1, and subtract. Okay, no big deal. And then what's the last instruction that we need to do? Convert it back. Well, if I can F move from S0 to W0, can I go the other direction? Sure. Okay, again, no data conversions happening here. It's just moving bits from one place to another. Okay, and that's it. Okay, all right, so that would be the initial estimate step. Okay, what's the one thing that's missing here? The Newton iteration, okay? But the Newton iteration was basically just some multiplication and addition, right? That's not too hard to program, I would hope, right? And then, how do I print it? Well, if it's an S0, a single precision float, how do I print one of those? Can I just print a 32-bit float? No. No. What do I have to do instead? Make it 64-bit and then print it, okay? And so F convert it from S0 to D0, basically, make it a double, and then load in a format string of wherever that is, and then print it, okay? Okay, so other than the Newton's estimate part, this is it, right? And you'll notice that if we go back to the real work of it here, okay, notice that in all of this, did we ever actually do a computation using any of the floating point instructions? Did we ever do a floating point square root, division, anything like that? No. Which means that this is very fast because it just did integer arithmetic, right? And bit shifting is really fast. Okay, so from a speed perspective, this is really cool. Now, I have lied maybe slightly because where would I be doing some floating point arithmetic? Step 4, okay? The improvement of the estimation has to be done with floating point stuff. There's no way around that. Okay, but if we go back and we look at what the form of Newton's method was here, okay, what do I have there? I've got some multiplications and I've got a subtraction and I've got this constant 3/2. Okay, is there any division there? No, there's some multiplication, sure, but there's no division. And that's good because what's faster in terms of floating point hardware, multiplication or division? Multiplication is much faster, okay, especially back in the 90s. Okay, I'm not entirely sure as to exactly the cycle counts or how long each of these steps would take on period hardware. Finding documentation from the mid-90s is not, and finding the info you want is not as easy as you might think. But anyway, okay. So yeah, so what you guys are going to do, okay, is do this, but in 64 bits. Okay, what's the one difference between doing this in 32? Well, what are the differences between doing this in 32 and 64 bits? Yeah, you're going to be using D0 instead of S0. It means that you don't have to convert for printing because it's already 64-bit. That's nice. Okay, but this number, this 5F blah, 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 is the number that you need if you're doing this in 32-bit. It is not the same number in 64-bit. No, and it's not just a bunch of zeros after it. Sorry. No, that doesn't do it either. Okay. All right. So I'll talk about that in a second. You have to look up what the magic constant is. Okay. And fortunately, there's a really, really fantastic Wikipedia page on this very thing. Okay, that's the number that we used for 32-bit, but it does give the 64-bit version. Let's see. Where? Yeah, here we go. Okay. So either one of those, um, two numbers, the 5FE6 blah blahs, those two. It's the exact value, the best you can get it is this one here. And Lamont, so actually there's links to a bunch of papers here, and I posted copies of a couple of them on Canvas in the files section. Lamont actually was a grad student up at Purdue in the math department when he wrote a paper about this, about, and that was in the early to mid 2000s, basically right when this source code had become available, and everybody dug into it and found this and was